In this video, I'd like to pick up where we left off following our meeting on Monday through Zoom. Normally, we are with each other for about an hour and 10 minutes, maybe a little bit longer than that on Mondays. And this week, we only had 45 minutes. So in the meeting, I was able to go over the course syllabus, the class expectations, and the design of the course, as well as the grading structure. But in this video, I'm actually going to do some discussion of physics itself. Many of the examples that I cover in this video will help you with this week's homework, although it may be necessary to consult the notes or the textbook for additional help and clarification if needed. Now, I would recommend that you have something to write with and write on, and copy the problems that I complete in this video, as well as other information that I may be jotting down on the screen. You don't have access to this presentation that I have on my screen, but the information that's contained within it might be helpful for you to reference later or to use on the upcoming exam. And do remember that all exams are open note and open book, so the notes that you take from this video can also be used on the exam. So here we go. This is Physics 151. This is the algebra-based physics class through Cincinnati State for the spring of the 2021 semester. Now, some of you are in this class just because it's required for the program that you're studying, but you may find an interest in the course itself and may want to consider studying it even further in your academic career. Physics in general is a study of nature, and that may not seem like an obvious description to you, because a lot of times when you hear students or people studying physics, you might be thinking about motion or collisions or something like that. But in reality, physics studies and can explain all of these things, not just motion and interactions physically that we can see on a large scale, but even on a very small, minute, even quantum scale. And so the more you study physics, the more you might recognize that it's physics that actually describes the behavior of the components within an atom. Physics can describe the behavior of outer space and celestial bodies at large. Physics is also used to describe the behavior of light, whether it's a particle or wave, as well as heat transfer. Now, this is a hot air balloon, and I think the image here was chosen to describe the nature of movement based on temperature shifts. And then, of course, the big one, what a lot of people recognize in physics, is the behavior of motion. And in this case, we've got a rocket that's being propelled upward with some amount of thrust. And we're actually going to start our class by studying kinematics, which is the study of motion. And so the most traditional sense of physics is what we're going to be beginning this course with. Within the chapter number 1, we hope to cover the following topics. We'll discuss measurements in units. We'll also be sure to be aware of scientific notation, special prefixes that are used with the units of measure. And a really important topic is going to be our discussion of unit conversion and making sure that we can do so accurately and precisely with an appropriate amount of clarity. We will also talk about the formal description of precision and accuracy, as well as uncertainty, the errors that we encounter when we round calculated results. And hopefully through Chapter 1, you'll learn a little bit about problem-solving strategy so that you can approach some of the more complicated examples and complete them on your own. So whether we're studying items at a very small scale or a very large scale, physicists generally use measurements to understand the natural world around them. And since we are in a physics class, we are talking about physical measurements, and all physical measurements contain two components. There is a unit component and a numerical component to every physical measurement. And you may have had math teachers in the past be real picky about you showing your units, or science teachers for that matter, showing your units with your results. And this is part of the reason why an answer to a problem can't, in this class at least, usually be represented by just a number, because the number is only a portion of the measurement that's necessary to provide a solution to a problem. So numerical values and units are very, very important when identifying solutions to problems or investigating situations in their entirety. For the most part, the units of measure that we're going to be referencing in this class is going to be the SI system of measurement. The SI system of measurements is sometimes called the international system. And while it's quite similar to, it's not really the same as the metric system of measurements. It's an extension of the metric system. And for the most part in our class, we're going to be using 3 base units from the SI system. And for length, we're going to be using the meter for our unit of length. For time, we're going to be using seconds as the measurement of time. And for mass, we're going to be using kilograms as our unit measure for mass. So lowercase m, lowercase s, lowercase kg for meters, seconds, and kilograms. And those are the main units that we're going to be using. And so you might be asking yourself, well, what about area measurements? What's the unit of measure for area? Well, an area measurement is simply going to be meters squared, or the product of a length times another length. Same thing with volume. In the metric system, the unit of volume is liters, but in the SI system, when we're talking about volume, we'll simply say meters cubed, or we'll just cube the length measurement. And so that may simplify things, and it may, I don't know, make things a little bit more complicated for you. But from my perspective, I think it's helpful to recognize that these are the 3 major base units that we'll be using. As far as the SI system goes in its entirety, there are actually 7 units of measure. And in other textbooks, you might come across this little diagram here. Of course, kilograms, measurement for mass. We've got meters, measurement for length, and seconds for time. A is an ampere for the measurement of electrical current. K is for Kelvin, the measurement of temperature. Moles for the amount of a substance. That's not really the same as a volume of a substance. It's Avogadro's constant number that counts the number of individual components of an item, which is often the number of atoms within an element. And then lastly, CD represents candelas, or how luminous an object is regarding its light output. And so advanced levels of physics will often involve all of these units of measure. For the most part in this Physics 1 class, we're going to be sticking with just these 3, meters, seconds, and kilograms. And as these units become used in more specific senses, different units of measure are developed. For example, the unit for power in the international system is known as the watt. And you've heard of watts before, I'm sure. You know, a light requires 60 watts of power to illuminate. Well, a watt is really just a combination of our 3 base units, kilogram meter squared per second cubed. Now, I'm not going to go out and say that this particular light bulb requires 60 kilogram meters squared per second cubed. So the watt measurement was defined and developed, and that seems to be the unit of power that we tend to use these days. And I, for one, am glad that it's there. This is quite a mouthful to say. And as I noted just a minute ago, the liter is a metric unit of volume, but it's not a unit of volume that we tend to use in this class. Instead, we're going to be using meters cubed or some variant of that to represent volume. Other systems, of course, do exist, and most prominently the United States, or sometimes called the imperial system, in which we use feet for distance, pounds for weight or mass, and fluid ounces for volume. And since we are in the United States and we tend to see those units pretty often, we will use them from time to time, and that also further explains the need for our ability to convert these units as well. Now, you will encounter very large and very small numbers in the world of physics, and understanding scientific notation is super important to report our results accurately. And you should recall that scientific notation is just a method for us to use to abbreviate numerical values. For example, the number 235 million meters is shown here on the right-hand side, and while that number is not too large or too out of control, it might be helpful for us to write that in exponential, or I'm sorry, scientific notation. And so at the end of the number there is an implied decimal point, and we're simply counting the number of decimal spaces that it would take to move that decimal right after the very first digit and in between the first and the second. So if we were to move that decimal point here in between the 2 and the 3, that was a total of 8 moves. And so we can report that as 2.35 times 10 to the 8th power. We're using a positive exponent here because the numerical equivalent of that is a very large number. So large numbers require positive exponents, and very small numbers require negative exponents. Now you might have other ways of remembering this, but often considering what's large and what's small is good enough. In this second example, remember we're trying to move this decimal point over here between the first digit and the second non-zero digit. So that's a total move of 3, 6, 7, 7 spaces. And that's why we've got our 3.97 times 10 to the negative 7th power. Now it's important to note that with the calculators that we're going to be using in class, and then also my own shorthand notation, you might see me write this a little bit differently, and I suppose you'll see others doing this as well. The number 2.35 times 10 to the 8th power might also be written as 2.35 capital E 8. And the number 3.97 times 10 to the negative 7th power might be written as 3.97 E negative 7. And so again, this letter E is really just one more way to abbreviate our numbers. Instead of writing times 10 to the 8th power, we can simply write E 8, or times 10 to the negative 7th power, we can write E negative 7. Now, I'm not entirely certain where the letter E comes from or why it's used. But again, many scientific and graphing calculators tend to utilize that. So if I turn on my graphing calculator here, the key that I'm referring to is this one. It shows a double E, and this is another weird thing about it, but it's a double E, but when you type that on the screen, it actually shows up as a single copy. So if I were to write 2.35 E8, 2.35 E8, so there's that capital E. It's a single E, even though it was a double letter E on the key itself. This should represent our 235 million. Also, I do want to point out that this capital E is significantly different than this lowercase e on this key here. So just be mindful of that and be aware of it. In fact, this calculator even adjusted that after I pressed the enter key, and it showed the full digits. Of course, we often use these abbreviations when our calculators can't display all of the spaces, or if we just want to save space with our handwriting work as it sits naturally. Now, you may also hear the phrase orders of magnitude, and that phrase simply describes a change in exponential value when you're talking about scientific notation. And by changing the exponent by a value of 1, that really changes the value of the total number, either 10 times larger or 10 times smaller. So when you hear that phrase, order of magnitude larger or an order of magnitude smaller, we're actually talking about 10 times the size, either larger or smaller. Now, if you'd like to pause the video on this screen and copy this down, here's another explanation. Here's another explanation of how the decimals should be moved, as well as some information on what you'd have to memorize in order to physically move decimals to identify scientific notation. And I'd also like to remind you, since I forgot to mention it earlier, that if you have downloaded a copy of our notes from the course documents, you'll see a lot of this information shared inside of that PDF document as well. So moving on, I've got an example here. If I have the decimal 0.00592 and I'd like to express that in scientific notation, which of these options is the best choice or the correct choice? Pause the video now and resume playback in a moment to check your work. Well, for me, I recognize that this is a very small number, so I knew that the answer had to be an exponential with a negative exponent. So I knew A and E was not a good choice. Then I recognized that the decimal had to be moved 1, 2, 3 positions to be placed in between the first and the second non-zero digits. Although this is sometimes a zero value. We always move this after our first non-zero digit. And that was 3 spaces, so I knew that option C and option D was no good, leaving us with option B. The slide prior discussed this notion of moving your decimal to the left or to the right and whether that's going to indicate a positive or negative exponent. And personally, I don't tend to think about that too much. I look at this number in general, recognize that it's a very small number, so we should have a negative exponent, and I tend to produce my result from there. But the nice thing about this course is that you can use whatever method that you're comfortable with as long as it's appropriate scientifically and mathematically. Now, sometimes we'll use specific prefixes to denote specific powers of 10. So you've likely seen these prefixes before. In fact, we use kilo or kilogram, kilo as our prefix for our SI unit of measure for mass. But really, this prefix business is just good for us to kind of speak about these numerical values more clearly. So, for example, if we've got this set of values here, some occurrence has taken 9,552,000 seconds to pass. And so as a numerical value, we might abbreviate that using scientific notation as 9.552 times 10 to the 6th, or 9.552 E6 seconds. Again, numerical and unit component of measurements, 2 components to every measurement. But here again, recognizing the exponent of 6, and that's the equivalent of the mega prefix that we saw back here, so times 10 to the 6th is the mega prefix, we could say that this object, or the length of time that passed, is not 9.5 million seconds, but it's only 9.5 megaseconds. And similarly, an object that measures 0.199 meters in length could be reported in scientific notation as 1.99 times 10 to the negative second power, or 1.99 e negative 2. Again, numerical and unit components of this measurement. Well, this negative 2, this times 10 to the negative 2, or this negative 2 here, that's the same as the prefix centi with the letter C. And so 1.99 times 10 to the negative 2 meters is often reported as 1.99 centimeters. And then lastly, in this example, an event that takes 0.0000015 seconds to pass. Clearly too many zeros here to report, so we're going to abbreviate that as 1.5 times 10 to the negative 5th, or 1.5 e negative 5 seconds. The exponent of times 10 to the negative 5, or the e value of negative 5. Oops, we had a typo in the example there. This is correct. It should be times 10 to the negative 6. The micro is another way to describe a millionth, which is a power of negative 6. So I should make a note to update this. This is not correct. We should have 10 to the negative 6th. So 0.1234515 seconds. There we go. Oh, wait a minute. I see what happened here. Okay. With my corrections, if there were supposed to be 6 decimal places, we would call this 1.5 times 10 to the negative 6th power, and that would be considered 1.5 microseconds. However, as it sits here, and I'll use a different color to make this stand out, 1.5 times 10 to the negative 5th seconds, there was no prefix for this negative 5, but if I move my decimal just one more time to make this 15, now my exponent would be considered negative 6, and that's where the answer that was listed here originally came from, 15 microseconds, and that's a Greek letter mu not a standard letter from our alphabet. So I guess that's a good talking point here. It's awfully nice when our prefix lands on a value that falls in this chart perfectly, but even if it doesn't fall in the chart perfectly, we can make some modifications so that we can report our answer using appropriate prefixes. Now, when it comes to unit conversions, which will have to be done pretty frequently in this class, there are lots of different ways to complete that. The textbook likes to use what are called conversion factors. And a conversion factor can be found in the unit conversions document that I made available in our course documents folder. And all of these numbers are conversion factors. For example, the conversion factor of 16 will allow you to convert between pounds and ounces with customary measurements of weight or imperial measurements of weight. And it would be up to you to decide whether to multiply or divide by 16 as appropriate when making your conversions. Similarly, if we're going from customary or imperial to metric, we've got other conversion factors that are available as well. And if you read along with the examples in our notes or in the textbook, you'll clearly see how they're using conversion factors to complete your unit conversions. When I'm in class sharing this technique or in this particular video, I'm going to use a process that's slightly different. And it's sometimes called the picket fence method. You'll see why in our challenging examples, or it's also sometimes called the T-chart method. And depending on who you've had for science at D. Russell Lee or at your home school, you may have seen this method already before. But me personally, I like this method, so this is the one that I'm going to be showing in class. Again, it doesn't matter which method you use specifically, as long as your work is appropriate. So in this particular example, we're being told that Angel Falls in Venezuela has a height of 979.0 meters. And this number, by the way, has 4 significant figures in it. So if you're familiar with that technique, keep that in the back of your mind. We're being asked to express this height in feet, noting that there are 3.281 feet in a meter. And this number also contains 4 significant figures. So when we do our math here, since both of these numerical values contain 4 significant figures, then our answer should contain 4 significant figures. More on that in another discussion. But here's the picket fence or T-chart method that I would use. I'm going to start with 979.0 meters, and I would like to convert that into feet. Now, fortunately for us, we were given the conversion factor here in this table, in this problem, but if we didn't have that, we could always refer to our conversion chart and find an equivalent value. In our chart, the conversion factor that might be used is down here. 1 meter is approximately equal to 3.28 feet, but we could have also used this conversion factor here as well. 1 foot is approximately 0.305 meters. And if you're using this T-chart method, then it doesn't matter which conversion factor you use. The end result will be remarkably close. Now, the whole goal with this T-chart method is that you're going to report this number, and again, you don't have to recall whether you're multiplying or dividing here. You're just going to report this number, which is a measurement in feet, in a position that will allow the unit that you no longer need to cancel. And the way units will cancel is by listing the unit one time in the top row of our T-chart and then once again in the bottom of our T-chart. So in this measurement here, I would like meters in the bottom and feet in the top because I know that there are a certain number of feet per meter. The 2 units are feet and meters. Since I want the meters component to cancel, I place the meter measurement in the denominator and the feet measurement in the numerator or the top of the T-chart. And now I'll report this number where appropriate. We're being told that there are 3.28 feet in 1 meter. 3.281 feet per 1 meter. If I didn't have this conversion factor given to me and I was doing this on my own, I might write 979.0 meters at the beginning of a T-chart. And according to this lookup over here, I might note that there's 1 foot in 0.35 meters. So again, I'm looking to have the meters component disappear, and I'm told that there's 1 foot, 0.305 meters. And the way the t-charts work is you simply multiply across the rows. So in this case, we want 979.0 times 97.90 meters times 3.281 feet divided by, well, there's no number here. We can imply that that was the number 1, no unit. 1 times 1 meters is 1 meter. And the simplified or reduced fraction that's the result here will be the converted length measurement. You should note that these values are multiplying across the numerator, and these values were multiplied across the denominator. So that does give us permission to cancel common factors. If there was an addition sign in between, we would never do that, but since this is all multiplication, we can. Meters will cancel with meters. We're going to end up with a result that's a numerical value over 1, and anything over 1 is just that numerical value. So what I tend to do at this point, after I recognize the unit that's going to be in my result, sorry, the meters are gone and we're left with feet, that's the only unit measurement that's left, I will reach for my calculator and create this fraction. So I'll turn on the calculator and I'll press Control Divide to make the empty fraction. And I'll substitute the numerical values into the fraction. You'll note that I can't enter the units in the calculator. That's for us to figure out on our own. But 9.790 times 3.281 over 1. When I press Control Enter, I end up with the result 3212.099. 3212.099. And that answer's okay, but it's not the best because it shows more than 4 significant figures. If you're familiar with significant figures, hopefully you'll recognize that the 4 that we'll keep are these here. 3212 feet is our answer. 979 meters is the same as 3,212 feet. And if I complete this unit conversion with a different factor, like I showed here in this example, we've got 979 meters times 1 foot divided by 0.305 meters. Again, the meters component will cancel, and we're going to be left with a measurement in feet. Resulting, or checking the calculator for this result, 979 times 1 divided by 0.305. That comes out to be 3209.836. 3209.836. Now again, on significant figures, the units of measure here contain 4 significant figures. This one only contains 3, so I should only report my answer with 3 significant figures. That would be the 3, 2, and 0, which of course when rounded becomes 3210 feet. And these two answers aren't identical, but they are awfully close. Now, I would be happy with either solution as long as you provide work along the way. If you show me how you arrived at your answer, I'm happy with either. If there is no work showing how you arrived at your result, then I'm not likely to award full credit. Here's another example. We'd like to express the speed limit of 65 miles per hour as a measurement in meters per second. So I'll start by building the t-chart, and I don't really know a conversion factor that will take miles per hour and transform straight to meters per second. And even if I look them up on the conversion chart, I don't know that there is a measurement for velocity or speed. So we'll just have to do this by hand hopefully without any reference to the conversion chart. I think you should be able to do this on your own. Now I'm going to tackle one unit at a time, and I'm going to try to take care of this miles component. So I'd like to make the miles measurement disappear, or component disappear. So I'm going to place miles down below, and I'm just going to think to myself, well, you know what? I know how many feet there are in 1 mile. I know that there are 5,280 feet per mile. So by using this conversion factor, I'll be able to change my unit of measure from miles per hour to feet per hour. But that still doesn't get me to meters. I'm trying to get to meters. So maybe I can think of another factor that will allow the feet components to cancel. And I remember from that last problem that there is 0.305 meters per 1 foot. And in the process of this t-chart, the feet components will again cancel, and now we're left with a measurement in meters. When I simplify the fraction, I will have a measurement of meters per hour. But that's not good enough. I want meters per second. So let's continue with this conversion. And this is where the t-chart really shines, because we can just keep moving along the way. Now I'd like to get the hour measurements to cancel, or the hour units to cancel. So since we had an hour measurement in the denominator, I'm going to place an hour measurement in the numerator. And I don't know how many seconds there are in an hour, but I can tell you that for every hour there are 60 minutes. And this is going to allow the hour units to cancel. And now I'm left with some unit of meters per minute, which again is not good enough. But with one more step, I think we can get there. I know that there are, let me say it this way. For every 1 minute, there are 60 seconds. So I'm going to report this unit conversion next. The minutes will cancel because there's 1 unit in the bottom of the t-chart and 1 in the top. And now I've got a series of units that will be left with meters in the top and seconds in the bottom of this chart. And all we need to do now is reach for our calculator and simplify. There's no need to list every unit component here, this value of 1. So I've got 65 times 5280 times 0.305 in the numerator and 60 times 60 in the denominator. I know that when we're finished, we're going to have a unit measurement of meters in the numerator and seconds in the denominator. And so here's a look at the calculator. The fraction on the left is what I entered, and the result that I have on the right, 29.0766. So 29.076, I'll round that to 7 meters per second. Now in math class, this would be a good answer because it shows 4 decimal places. However, for this class, we should be considering significant figures. And again, I'll explain this further in another lesson, but we've got 2 significant figures in this number. We've got 4 in this one, 3, 2, and 2. And so the least significant measurement appears to be these with 2. And so therefore, I'm going to report my answer with 2 significant digits or significant figures here and here, 29. That does not need to be rounded, so we'll call this 29 meters per second. Let's try just 2 more unit conversions, and we'll wrap up this particular video. The dimensions of a football field are 360 feet by 160 feet. I believe this includes end zones and sidelines. What is the area of the football field in square feet? Well, part A should be pretty easy for us. 360 feet times 160 feet will yield a result with a numerical component, 360 times 160, and a unit component of feet times feet. Now the measurement feet times feet, as with any variable, will simply add the exponents. So we've got feet to the first power and feet to the first power becoming feet squared. That's where that result tends to come from. And 360 times 160 results in 57,600 square feet. And if we were talking about decimal points here, then we would have had 3 significant figures times another 3 significant figures. Our result can contain 3 significant figures that we show here. So part A is done. Part A, 57,600 square feet is a good answer. But what if I want to convert that into meters? Well, I would still use a t-chart for this, but we've got to take it just a little bit farther than usual. So the beginning of the t-chart looks like it would normally, 57,600 square feet. But as far as unit conversions go, I'm going to have to place a measurement of feet in the bottom, and I still remember that unit conversion of meters. 0.305 meters per foot. But in completing this conversion, this measurement of foot will cancel just one of the feet measurements back here. Remember, this was feet times feet. And even though I wrote it as foot squared, we can think of it as feet times feet. So only one of these will cancel with the numerator and the denominator. How do I get the other one to cancel? Well, it's easy. Just do it again. We need another foot measurement to cancel. And I'm also going to use that same meter conversion, 0.305 meters. 0.305 meters per foot. Well, now this foot measurement can cancel with that foot measurement. And what are we going to be left with but meters and meters? What happens when we multiply meters times itself? Well, we end up with a measurement meters squared, which is exactly what we're after. So this is good. All we need is 57,600 times 0.305 times 0.305 again. And reading the calculator off screen, I get 5358.24. Assuming three significant figures here, here, and here, our solution should only have three significant figures, which occur at the beginning. This 5 will need to be rounded, and we'll say 5360 meters squared. 5,360 square meters. And so to wrap up this video, let's just quickly summarize here. Measurements must have the same units before they can be added or subtracted. Units don't have to match when you multiply, although it tends to help when they are the same. But it is important to note that measurements from different families or different types of units cannot be added or subtracted. So for this final question, which of the following pairs of units may not be added together even after unit conversions have been made? So pause the video and think about that. A, B, C, D, or E. Which of these pairs in no way can be added together even if you were to convert some of the units? Well, hopefully you recognize that it's option B. Seconds and pounds can never be added together because they come from different families or different types of units. For example, feet was a measurement of length, centimeters was a measurement of length, hours and years are both measurements of time, grams and kilograms are measurements of mass, meters and miles, again, are lengths. So in all of those other cases, you can convert feet to match centimeters or centimeters to match feet and so on, and then those measurements could be added together. However, with seconds and pounds, a measurement of time and mass, these two types of units cannot be added together. So no matter what conversion factors you may apply, the value from one measurement in seconds with a value of some other measurement in pounds can never be added or subtracted. So this concludes this particular video. I am going to record one more, and I understand that these are getting a little bit lengthy, but it is necessary for this first week since we had our first meeting on Zoom, and we spent so much time covering the syllabus and the expectations for the course. Thanks for watching.